This is the third video in a series of videos I'm making about iteration dynamics and Newton's method in this computer program that we see here called Mathematica. I do it for my Calculus 1 students. It's their project number 1, but if you are not a calculus student of mine, I hope you can get benefit from it. You will want to watch the first couple videos though, where I do go through, especially these first couple sections here, the introduction and how to iterate on a TI graphing calculator. You should make sure you spend the time in looking at those first two videos, doing some experimentation to confirm what we saw. In this video, I'm going to review what we saw in those first couple videos, in these first three examples, and then I'm going to do something new. I'm going to try to talk about a graphical method for understanding what we observed numerically. So the situation here for example 1 is the function that you iterate is f of x equals 0.2x plus 5. What does it mean to iterate? It means to start with an initial condition, a seed, like x0 equals 3. Take that as input for the function, plug it into the function to get an output. 0.2 times 3 is 0.6, 0.6 plus 5 is 5.6. Then you take that output, 5.6, and make it your new input, plug it into the function again. Take 0.2 times 5.6 and then add 5. What do you get? Well, you could try that with your calculator, but I can use Mathematica here, nest list. When the function is 0.25x plus 5, when I define it this way, and then use nest list in this way with the function that you iterate right there, the seed right there, and the number of iterates right there, you can see the values first are 3, then 5.6, then 6.12, then 6.224, etc. And eventually it seems like the iterates equal 6.25. Actually, that's an illusion. They're just approaching 6.25, and Mathematica is just rounding. They never actually equal 6.25. If the seed is, so with that seed, the iterates increase to 6.25 then. If the seed is bigger than 6.25, like 20, then the iterates decrease towards 6.25. This even works with really big numbers like a billion. The iterates there decrease towards 6.25, and negative a billion, the iterates increase towards 6.25. If the seed is exactly 6.25, then you get exactly 6.25 all the time. That is a fixed point. It stays fixed. We could confirm this another way by making this 0.2 a 1/5 and changing the 6.25 to a 25/4. It always stays exactly equal to 25/4 in that case. Let's go back to a decimal. So that's what we observed. No matter what the seed is, the limit is 6.25. I added this sentence to what I had before. I put a limit symbol. It's a limit of a sequence, x0, x1, x2, x3, etc. Those numbers form a sequence, and as n goes to infinity, the sequence outputs approach 6.25, though they never actually equal 6.25 exactly unless the seed is 6.25. Next example was f of x equals 7x minus 4. We saw that 2/3 was a fixed point. If you plug in 2/3 exactly, you always get 2/3 out. If you plug in a number just barely bigger than 2/3, the iterates go off to plus infinity. They don't approach 2/3, so this is different. If you plug in a number just barely less than 2/3, they go off to minus infinity. So 2/3 is a fixed point like 6.25 was for example 1. However, it's a different kind of fixed point. You might call this fixed point up here an attracting fixed point because it's attracting the other seeds. And you might call this one 2/3 repelling because if you start just barely away from 2/3, the iterates go away. That's a repelling kind of fixed point. I added some sentences here. No matter what the seed is other than 2/3, the limit is either plus or minus infinity. In fact, if the seed is bigger than 2/3, the limit is plus infinity, and if the seed is less than, I should have said here, less than 2/3, then the limit is minus infinity. It doesn't mean infinity and minus infinity are numbers. They're not numbers. This is just notation, standard notation, meaning here the sequence, when the seed is bigger than 2/3, gets bigger and bigger without bound to the right, positively, and when the seed is less than 2/3, the sequence terms, the numbers get smaller and smaller without bound to the left. Alright, what about this example? The function was x squared minus 1. We saw lots of different kinds of behavior with this one. Some of it cycled back and forth between -1 and 1. Some of it eventually cycled between -1 and 1, -1 and 0, excuse me. When the seed was exactly 1 plus square root of 5 over 2, that was a fixed point. But seeds slightly different than that went away from that, so evidently 1 plus square root of 5 over 2 is a repelling fixed point. This one ends up going close to the 2 cycle between -1 and 0. This one goes off to infinity. Same kinds of things happen if we plug in the corresponding negative numbers, which are negative. The negative of 1 plus square root of 5 over 2 is not a fixed point. So we're not seeing fixed point behavior here. Actually, they become positive right away and get close to the original fixed point. 1 minus square root of 5 over 2 is also a fixed point. And if you plug in seeds that are close to but not equal to that, they go away. It's evidently a repelling fixed point as well. And in this case, they both approach the 2 cycle -1, 0, -1, 0. All right, now the new stuff. What do I have down here? I've got essentially a little Mathematica program that I made with this command called module that can be used to make little programs. I'm creating a new Mathematica function that I'm calling CobWebPlot. And this function has a number of different inputs. It's got the function that you're going to iterate. And this is the way the syntax goes. If you don't know much Mathematica, don't worry about it. If you do know Mathematica, you might want to try to understand this. That's the function you iterate. You put an underscore to emphasize it's going to be the input for this CobWebPlot function. These two things here are emphasizing the window in the graph I'm going to make, both the x and min and x max values and the y min and y max values. The x and y themselves are not technically necessary for me to put in here, but I'm just doing it for clarity when we use the CobWebPlot code here. The seed will go in this spot and the number of iterates will go in this spot, although I do know actually in experimenting with this code that the graph you see is going to contain one more iterate than what I actually put here. So you can enter this code and then you can use it. So we use it down here for example 4. For example, first we use the function 0.2x plus 5. How do you use the CobWebPlot? You just go ahead and type CobWebPlot. Then you look at the syntax up here and enter these things without underscores. The function name, comma, the window in the x direction. Let's see, the fixed point for this one was 6.25. So if I went, for example, between -1 and 10 in both the x and y directions, that might be a pretty good window. Let's pick a seed of 0 and let's do 1 iterate at first, although it's going to really show 2 iterates in the graph. All right, here it is. Here's the output. The output is twofold. First of all, there's a list that indicates the seed and the first iterate. When you plug in 0 into this function, you do get 5 out. This is not the 0.05, although this point right here on this red graph is the 0.05. What do we see with this graph? We see this blue line, which is the line y equals x. Listen real carefully. We see the red line there, which is the graph of y equals 0.2x plus 5, the function we are iterating. And what this graph is showing, this CobWebPlot is showing, is a graphical way of understanding what the iterates are doing. When I plug in x equals 0, what I can imagine doing is starting on this blue line, at this point, the origin, where x is 0 and y is 0. When you plug x equals 0 into the function, you get 5 out. That's the second coordinate of this point. You go up to the graph, to the red graph, and look at the second coordinate of that point. It's 5. That is the next iterate. That's x1. That's the output of the function when x0 is 0. Then, instead of going back down to the x-axis, it's fun and enlightening to go over horizontally to the blue line, y equals x, because now this point has coordinates that are both 5, 5, 5. And you can now find the output at x equals 5 by going up to the graph, to the red graph. Second coordinate at that point looks like it's 6. Is that the next value? Yes, if you plug in a 2 here, you'll see 6 for the next iterate. That is the second coordinate of this point. Now repeat. Go over to the line y equals x. This point has coordinates 6, 6. And then go up to the graph, the red graph. The second coordinate is the next iterate, 6.2, etc. And you can see, because of the nature of these graphs, because of the fact that the red graph crosses the blue graph with a slope less than 1 there, and also bigger than 0, that it forms a staircase. So you might want to call it a staircase plot instead, but there's a good reason it's called a CobWebPlot we will see later. It forms a staircase that is forced to head toward this point of intersection between the red and blue lines. What is that point of intersection? It is 6.25. It is the fixed point. In fact, I can use a built-in Mathematica command called solve to confirm that. Where do f of x and y equals x intersect? Solve this equation f of x equals x for x, 6.25 is the answer. That is the fixed point. If your seed is, again, bigger than 6.25, like, well, let's pick 10, now your iterates go down towards 6.25, and you can see with this staircase approach where you start on the blue line, go up or down to the red graph, go left or right to the blue line, go up or down to the red graph, etc. You are forced toward this point of intersection. You are forced toward this fixed point, this attracting fixed point at 6.25. What about the next example? When the function is 7x minus 4, the fixed point there was 2/3. Maybe I want to make my window bigger here, I think. Start with a seed very close to 2/3, like 0.67, and iterate. Let's go 5 iterations. What do you see? Now you see the iterates, these numbers, going away from 2/3. 2/3 is a repelling fixed point. 2/3 is the intersection point of the red and blue graphs. Remember, the blue graph is y equals x. The red graph is now y equals 7x minus 4. These points are moving away. You start in the blue graph, you go up or down to the red graph, left or right to the blue graph, up or down to the red graph. In this case, it's up and right all the time. We are now forced to go away from that point of intersection, and that's why it's a repelling fixed point. That's a graphical reason for that. If we start just less than the fixed point at 0.66, now these points go off to minus infinity. We started just left of the intersection point. We start on the blue graph, y equals x. We go up or down, in this case down to the red graph, left or right, in this case left to the blue graph, etc. You repeat the process and you can see visually why you're going away from the fixed point. Finally, let's look at the x squared minus 1 example. And here I think we're going to want to go in close. And let's start close to the opposite, actually the fixed point that was 1 minus square root of 5 over 2. That was what, about negative 0.61804. Let's just do negative 0.62. Not really quite close enough to see it real well. It's close to the fixed point there, which is 1 minus square root of 5 over 2. Let's go more iterations. How about 10 iterations? Now we can see a little bit something bigger there. Let's go 20. That's interesting. Now, by this process of starting on the blue line, going up or down to the red graph, and then left or right to the blue line over and over and over again to see the graphical nature of the iterates, we're spiraling away from the fixed point at 1 minus square root of 5 over 2. And there's an oscillation up and down. And this is sort of looking a little bit more like what you might call a cobweb. Keep going. The iterates are eventually approaching the 2 cycle between -1 and 0, and ultimately that means they're approaching this rectangle shape, the outer rectangle, whose coordinates are always -1 and 0. We're approaching that 2 cycle. Okay? That was pretty quick. We'll talk about the CobWebPlot more in the next video.